Now let's take a look at OSPF's metric calculation. For example, let's see our force routing table. So we have some inter-area routes. For example, if we want to get to 10.0.23.0/30 subnet, the route to get there has a cost of 3. To reach this network, the 10.0.12.0/30, it has a cost of 2, which is logical. It's less by 1 hop. OSPF uses interface bandwidth to calculate its metric, which is called cost. The cost equals the so-called reference bandwidth divided by the bandwidth of the given interface, and the default reference bandwidth is 100 megabit per second. These are 1 gig links, so their cost should be 100 divided by 1000, which is 0.1, but it can't be less than 1, so it's rounded up to 1. So again, from R4 to get to R3, this link has a cost of 1, this link has a cost of 1, and this link has a cost of 1. So the total cost is 3. And to get to R3's loopback address, which is this row, we need to add +1 to the total cost. So it has a cost of 4. What we want to do now is we want to change the reference bandwidth on every router, because we can't really differentiate anything above 100 megabit, because every interface will have the cost of 1. So let's change the reference bandwidth to 100 gigabit per second, for example. So even if we had 10 gig SFPs, we still have space to improve. The command is, and we need this to issue under the OSPF process, is auto cost reference bandwidth, and we need to define this value in megabit per second. So 100 gigabit per second is 100,000 megabit per second. And there is a warning message. Please ensure reference bandwidth is consistent across all routers, which is what we want to do. So I'm gonna do the same thing on every router. And we will see what has changed in the routing table. Show IP route. So just as we expected, the total cost has changed. Now it has a cost of 300 to get to R3 and +1 additional cost to reach its loopback address. Now what if I change the bandwidth of R2's G01? That should influence this cost to reach R3. So let's change the bandwidth to 100 megabit per second, for example. So on R2, interface G0/1 bandwidth, and we should give this value in kilobits: 1 megabit, 10 megabit, and 100 megabit. So this should have a cost of 1000. So the total cost should be 100 plus 100 plus 1000, which is 1200. So let's check it. R4 show IP route, and that's what we have expected. And remember to add 1 additional cost to get to its loopback address. I'm gonna change it back to 1 gig. we can also define the cost directly with the IP OSPF cost command, and the value 500, for example. So now the total cost should be 100 plus 100 plus 500. So this should be 700. Let's check it. And let's change back to the default. Now, what if I set another AVR? Like this. Now we have redundant connectivity towards R3. We are going to call this R5. So I'm gonna quickly configure R5 as an area border router, and we will check the routing tables again. So which routes do packets take by default to get to R3? On R5, let's check the routing table. It looks like we take this lower path to get to R3. This upper path is not even present in the routing table. Just to prove that, let's run a trace route from R4 trace route to 3.3.3.3. See, 14.1, which is R1, 15.2, which is R5, and 35.1, which is R3. Although it is not present in the routing table, both routes are present in R1's LSDB. So let's see that. Show IP OSPF database. So we have link state advertisements from both R2 and R5. Both of them provide us type 1 router LSAs and type 3 summary LSAs. So these are just routes from area 2. See, these are the prefixes 23.0 and 35.0. So both of them are just advertising these. And we have even a type 2 network LSA from R5. So according to this, R5 should be the designated router on this link. So let's check that. Show IP OSPF neighbor, which is true, but the reason why this route is not present in the routing table is that it has simply more cost. Remember that I didn't change the reference bandwidth on R5, so to get from R4 to R3, this link has a cost of 100. This link has a cost of 100, but this link has a cost of 1 plus 1 additional to get to its loopback address. So the total should be 202. So with OSPF, we don't have the possibility to load balance between these paths if they don't have the same cost. So unlike EIGRP, OSPF doesn't support unequal cost load balancing, which sometimes can be a nice feature. But we do support equal cost load balancing, or ECMP, if we have the same costs. So now let's change the reference bandwidth on R5 to 100 gigabits. So router OSPF 1 auto cost reference bandwidth 1 gigabit, 10 gigabits, 100 gigabits. And now to get to R3, both paths has the same metric and we can do ECMP or equal cost load balancing. So let's prove that. So now both paths are present in the routing table. 15% of the traffic will take this path and the other 50% will take the lower path. But unlike EIGRP, we can't really do load balancing if the metrics are not the same. And by default, we support 4 paths, if I remember correctly. We can configure it under the OSPF process. And the command is maximum paths. And I am not sure, but I think the default value is 4. So I could add 2 more ABRs here by default, and each of them would take 25% of the traffic by default.